And this is the series that we encountered by accident this week when I had not read the section I asked you to read in your statistics book, and it turned out it had a little bit of calculus in it, and we ended up talking about calculus for a little bit, finding areas under curves. And this series arose finding the area under a parabola.
Yes.
That we were looking at. And do you remember? Actually, you did when we were talking about it. Do you remember now what the value of this sum is for a given n?
I think it's n times n plus 1 times 2n plus 1 over 6.
Am I still on camera here with the 2n plus 1?
Yes, you are.
Okay. N times n plus 1 times 2n plus 1 over 6. So let's do the same thing to check this. Let's check it for 1, or it just should add up to 1.
So we get 1 times 2 times 3 divided by 6. 6 divided by 6 is 1.
Alright, let's check it for 2, where we should add up to
5, looks
Okay.
like. Okay, so we have 2 times 3 times 5 divided by 6. 30 divided by 6 is 5. Alright, I guess we can do it for 3. So that should add up to 14.
Okay.
So 3 times 4 times 7. So 12 times 7. So 12 divided by 6 is 2 times 7, which is 14.
Okay. Alright, cool. So we made these blocks, and we're going to try to see if we can find a geometric argument for these blocks, but we're going to do that in the next video.
Okay.
First, I want to ask you, first I want to try not to sneeze, and then second I want to ask you, this side's always an integer, right?
Yes.
Which means if this formula is true, this side should also be an integer.
Yep.
So why is n times n plus 1 times 2n plus 1 always divisible by 6?
Well, let's see. So that means it has to have a power of 2 in it and a power of 3 in it, at least one of each. So starting with the power of 2, we can see that we have an n and an n plus 1. That means if n is odd, then n plus 1 is even, and if n is even, that solves our problem.
Okay, great. Very good argument. So we needed a 2, and we get the 2 because one of n or n plus 1, since they're consecutive integers, that has to have a 2.
Alright, so let's see. Then multiple of 3, we can look at what is n mod 3. If n is 0 mod 3, then that solves it. We have our 3 in our 2, but if n is, say, 1 mod 3, then these two terms aren't, this term is 2 mod 3, but this term we get 2n, which is 2 mod 3 plus 1, so 0 mod 3.
Okay.
And if n is 2 mod 3, then this term is 0 mod 3 because we're adding 1 to it.
Very good. That's great arguing. So even though maybe at first glance it doesn't look like this will necessarily always be an integer, in fact it is.
It has to be, yep.
So that's really good. Do you know, we're going to look at the geometric argument in a minute, but do you know how to prove this without a geometric argument?
I think it would have to involve these sums somehow. I don't think I would know how to do it.
Okay, well that's fine. That's fine. I will, maybe at the end of this project I'll show you an idea how to do it, or maybe we'll just stop after the geometric part of it.
Right.
Alright?